Imagine a single particle moving through an empty void. It is traveling at a constant speed in a perfectly straight line. Does this object have angular momentum? It isn't rotating, and its path has no curve. When we hear that term, we usually picture a rotating planet or a spinning top. We instinctively associate it with things moving in circles. But watch what happens when we drop a fixed origin point, let's call it O, into this empty space, set safely apart from our particle's trajectory. From the perspective of that specific dot, this straight-flying particle actually possesses a measurable amount of angular momentum. Angular momentum is a relationship. It describes an object's motion relative to a specific observation point. Physicists often refer to angular momentum as the moment of linear momentum. Let's break down exactly what that means. This graphic shows the mathematical definition. L equals R cross P. Here, L stands for angular momentum, and the cross signifies a vector cross product. A cross product is a mathematical operation that multiplies two directional arrows to produce a third arrow perpendicular to both. The P represents linear momentum. That is simply the particle's mass multiplied by its constant velocity. The R is the position vector. It is an arrow connecting our chosen origin point directly to wherever the particle happens to be at that exact moment. When you calculate the cross product of R and P, the math generates a brand new vector. This one sticks straight out of the flat plane formed by the particle and the origin, exactly at a 90-degree angle. The length of this new vector tells you the magnitude of the angular momentum. It represents how fast the particle is sweeping past the observer's field of view. There is a catch here. As the particle flies down its path, its distance from the origin changes. The angle of that position line changes too. Yet, the angular momentum stays perfectly constant. This diagram illustrates the particle moving along its straight line. The position vector forms the hypotenuse of a right triangle, creating an angle theta with the line of motion. If we apply basic trigonometry, the term r sine theta gives us the length of a line drawn straight from the origin, perpendicular to the particle's path. Notice what happens as the particle moves forward. The position vector r gets longer, but the angle theta gets smaller. These two changes perfectly cancel each other out, meaning that perpendicular dashed line never changes length. The particle's mass is constant, its velocity is constant, and that perpendicular distance is constant. Because those three factors never vary, the total angular momentum of this straight-flying object is locked in place. It is a mathematical consequence of the track's offset from our vantage point. So, what happens to the math if we pick up our origin point and put it somewhere else? This diagram shows what happens if we drag the observer further away from the track. That perpendicular baseline gets longer. As a direct result, the calculated angular momentum increases. Conversely, if we step closer to the flying particle, that baseline shrinks and the total momentum drops. In this diagram, we place the origin point directly on the particle's path. The angle between the position vector and the velocity vector becomes zero. The perpendicular distance collapses entirely, and the angular momentum zeroes out. The particle hasn't sped up, slowed down, or altered its course. The only thing that changed was where we decided to stand. Angular momentum acts as a mathematical bridge linking linear velocity to a rotational reference frame. It shows us that in physics, spin relies heavily on where you are looking from.